So I'm standing next to one of our testing machines. This is called a Foursquare Dyno, or a power loop dyno. The theory behind a power loop dyno is that the motor spins the drive shaft, and there's two transfer cases of opposite hands. So there's a left hand and a right hand transfer case where the inputs are connected together and the front outputs are connected together, and torque and power are running in a loop. The only power required to drive that system is the frictional losses in the gears and seals and bearings. So we can induce a high amount of horsepower with a small power motor. Using this machine, we can run approximately 300 horsepower in a loop for many hours during the day without putting the transfer cases in a vehicle and taking them out in the field. We can monitor temperature, we can monitor noise, vibration, all the sources that might indicate a problem is happening right here in the shop. One of the unusual tests that we've run on this machine is oil fill capacity. You may have noticed in the Atlas transfer case manual that we specify 2 quarts for every single Atlas, regardless of gear ratio and rotation. So one of the things we're testing on this is whether or not less oil will actually reduce the transfer case temperature because of the churning and aeration of the oil due to the gears dipping and splashing oil everywhere. It might seem counterintuitive that less oil would actually result in a lower temperature, but it's proving to be well documented that too much oil can result in much higher transfer case temperatures. As an engineer, one of the things that we need to do is test, because we don't all the time have 100% certainty on a particular design, how it's going to perform from a material standpoint, from a heat treat standpoint, from a stress concentration standpoint. And at Advanced Adapters, one of the ways that we do that is by using material test blanks in a torsional failure machine. All these broken samples here represent material test blanks of different heat treats, different materials. Primarily, they all have the same geometry because we want them to break at the same spot each time so that we can make an accurate comparison between all those different variables. So this is our torsional failure machine. This was created in conjunction with Cal Poly as a mechanical senior engineering project. The machine consists of a headstock, which is the driving side, and a tailstock, which is fixed. Test samples and shafts can be placed in here and broken under torsion. This unit is powered with 2 hydraulic rams that pull on a 40,000 pound working load chain that induces torque into the headstock. Using a computer, we pick up 2 different pieces of crucial data that we need to understand the materials and heat treats a little bit better. One is torque, and we're actually measuring a linear force with this load cell that's calibrated for this whole assembly, and the computer actually converts the force into torque. The other is angular displacement, or particular degrees that the shaft moves under torsion. And that's picked up on an encoder on the other side of this shield here. The torsional failure machine is controlled by a computer. The computer collects the data and graphs it for us so that we can analyze the results of the different heat treats and materials. Once the data is collected, we graph the results, and from there we can make comparisons on different materials and heat treats to understand their various torque capacities and stress limits. We're going to break an Atlas output shaft. This is a particular sample that failed in heat treat, and so we're actually going to see what happened by breaking it. We're going to check out the various torque capacity versus what we know that it should be. The shaft is fixtured in the headstock, and then the splines are captured in the tailstock, which is fixed, and we should see a breakage somewhere in this location. This particular sample broke at about half the capacity of the torsional failure machine, which is about 15,000 foot-pounds. So this is the data collected from the sample that we just ran. In the upper graph we see torque, and the bottom graph we see deflection. I will take these two pieces of data and then we'll plot them in this graph that we saw earlier, and then we can analyze the results. So we just ran an ultimate failure test on this shaft, and that's only one aspect of design that we're interested in. The other aspect is torsional fatigue. And in torsional fatigue, the machine will twist the shaft one direction to a certain specified torque, then twist it back the other direction. And as the engineer, it's beneficial to know how many full cycles you can complete before the shaft breaks in fatigue versus an ultimate failure.